Swayam Prabha. Digital India. Educated India.
Welcome to this session. Having seen the basic operation of the charge pump PLL and this small signal block diagram, we need to now look at some nitty-gritties of this charge pump PLL. And what we are going to see that the blocks which we thought are well behaved earlier, they have some problem and we need to fix that. So, the first one is, again just to give you a quick block diagram which we have been studying, that you have a charge pump. I will just writing this is like this. You have this loop filter followed by VCO and fed it back. Okay. So, this is your reference and this is your output. Now, given the reference and the output signal for the PFD, what happens is that when your reference signal comes very close to your out signal, right, very close. So, this error may be, phase error may be much lesser, but is still there. Okay. May appear that it is 0, but it is not 0. So, in response to this phase error, what we have is up goes high and it will come back as out signal goes high. So, this is the kind of up and down signal which we have. The problem with this kind of PFD is the following, that when we use this up and down signal to clock our charge pump. Where was our charge pump? Our charge pump was something like this, where we have the switches and this is up and down, this comes here, right, both are ICP. So, these up and down pulses. So, just to tell you that the up pulse which is coming here is a very narrow pulse. Okay. If you have very small phase error, then you are going to have a very narrow pulse which clocks these switches connected to up and down. So, what will happen is that these up and down signal, see up and down at the end, they are switches. They may be realized using MOS switches, like either for PMOS or NMOS. If you give in any given technology, if you give this pulse to the MOS switch, right, it will not, even if the pulse width is very narrow, then it will not even turn on. If it does not turn on for a small phase errors, then what it means is that ICP, the current which you are going to get out of the phase error detector, that current will remain 0, it will not change. Okay. So, if the current does not change, then you can say even in the presence of the phase error at the input of the PFD, the PLL is not correcting for the output. Okay. So, there exists some region near the 0 phase error in PFD block which we have seen so far, that your output does not change. What was the PFD block which we saw earlier? There were 2 D flip flops, both were both input were connected to VDD. One was clocked, you can say, with reference, other was clocked with out. In our case, the output of these blocks are up and down, and they both were used by the AND gate to reset the outputs. Okay. So, the up and down pulses which we have here, they are so narrow in this particular implementation that your switch cannot turn on, which will now give a different characteristics for PFD plus charge pump. So, earlier we saw PFD characteristics like up, minus, down, average versus phase error. Previously, our characteristics were something like this, okay, from minus 2 pi to 2 pi. Now, if we are looking at the combined characteristics of the charge pump, then you can say this is up minus down average times ICP. It's also it will just have the multiplication factor there. Now, as per our initial PFD analysis, for ideal PFD analysis, the characteristics will look like this, but what happens because it does not respond to phase error near 0. So, the output of PFD plus charge pump is 0. Okay. And then it's when you have large enough phase error, you will surely have a linear response. Okay. So, here we are only saying that you need some minimum time for this pulse to turn on the switches. Okay. So, that minimum pulse time, if you do not give that minimum pulse time, you will have error, and you can think about it that minimum pulse time is whatever you are seeing here, right. So, this is kind of the plus minus T min which you need to have in your pulse width to correct for the phase error at any given time, right. This region of operation in the PFD which we have seen so far is called as dead zone. Okay, it's like PFD is literally dead, it is not responding. Okay. So, then we have to come up with some ways to get rid of this dead zone, right. So, to overcome this dead zone problem, what we do is the following. Let me just rewrite it. Your new up, this is, let us say this is old up and down signals. What we do in then improve PFD or the PFD with removal of up and down, we make our pulse on for at least T min time which is required to turn on our switches. So, just look at this. So, when I get my reference pulse high, my up will go high like this. Okay. Whenever I get pulse on out, my down pulse will also go high, and both the pulses will remain high for T min time. And then both will come down. Okay. So, this is T min period for which both the pulses up and down are high. It is also called as overlap, where T up and down pulses overlap each other. This is the region. Okay. So, in response to this, if we somehow we can implement it, you will see your ICP, if I provide minimum time for the switch to turn on, then current will also flow for now. So, what we have here is our ICP goes high and it remains high for this time. Okay. And then as, so just look at this, when up pulse goes high, your switch closes, you get the current here ICP. Then down pulse comes, this also closes, right. So, the ICP which was flowing earlier into the loop filter, now that flows down. You can look at it multiple ways, that you have a direct current path of for ICP from top to bottom, right. So, no current flows to the loop filter, but in the charge pump the current flows, and that current flows from top to bottom. Okay. So, even if you think about it, that your phase error is actually equal to 0. So, when your phase error is equal to 0, even then in that particular case, let us just take another example, that when I have phase error equal to 0. So, both the edges are aligned. In response to this, I will have my up pulse going high for a minimum of T overlap period and come down. Similarly, I will have my down pulse going high for the same amount of time and coming down. So, your charge pump, both the switches get closed for 0 phase error. You have 0 current going into the loop filter, but current flowing from top to bottom in the charge pump. Okay. So, in this way you can get actually get rid of your dead zone problem. Now, how we can implement that thing in circuit? Well, what we actually need here is the following. Whenever our down pulse goes high or the second pulse goes high like this, both the pulses come down only after minimum amount of time. So, if you look back at the circuit here, which we have been using for PFD, right. So, in this case, a pulse goes high and then I have to wait for some time. Okay. So, what you can do is the following. My up pulse goes high, and the down pulse goes high. So, the end output becomes higher, which is going to reset. So, what I do? I introduce a delay of value T overlap. Delay TD is equal to T overlap. If I introduce the delay in this path, then as soon as this goes high, when this particular thing goes high, right, NAND output will actually go high, and when NAND output goes high, the delay, because of the delay here, the reset pulse is delayed. Okay. So, when reset pulse comes, so what we are doing here is, I will just draw the reset also. So, ideally the reset is coming at this node. As soon as reset goes high, your outputs will go low. So, you delay the reset such that this happens, and how you can do that? By introducing a delay in the feedback path, right. So, in this way you can get rid of the dead zone problem in the charge pump. Okay. Thank you.